In this video, I just want to take a couple of minutes and briefly discuss interpreting correlation. And so let me just kind of get a title up here. So interpreting correlation. So we've discussed at this point, and if you haven't watched those videos yet, how to do the hand calculations, scatter plots, what linear relationships and curvilinear relationships kind of look like. And just kind of as a way to recap and get us all on the same page, remember if r equals positive 1.00, then we're saying we have a perfect positive relationship. And so this would look something like this, where all the dots would be kind of right on the line. And if r was negative 1.00, we would have a perfect negative relationship. And so in this particular case, just a quick sketch here, you would have something to look like this. And again, all of the dots would be right on the line. And so when r equals 0, again, we know that we have no relationship between the variables. So I'll just write that, r equals 0, no relationship. Okay? But when we're interpreting this, we need to make sure we understand that we're not sure of causality. In other words, an old axiom here, correlation does not equal causation. All correlation is doing is saying that two variables, a variable x and a variable y, for a particular set of individuals, are related to one another. And so when we say that they're related, three kind of things could be actually happening. Okay, because we're talking about covariing, right? That x and y are covariing with one another. That's what we're saying. If there is a correlation, you're saying there is a lot of covariation. As x is increasing, y is increasing. They're covariing in the same amount, or as x is increasing, y is decreasing in a similar amount or fashion, and that covariance is allowing us to have this R value. And so when we know that they're covariing like this, we don't know if causation is actually occurring. And so you kind of have three interpretations. One, X could be causing the variation in Y. So X could cause the variation in Y. Two, Y could cause variation in X. Or you could have the third option, kind of a third factor. Maybe it's factor Z is causing variation in X and Y. This makes a lot of sense if you think about it. So you just think of a generic, if we were to kind of show a scatter plot of, let's just say, and I'm just making this up, but let's say that a variable Y, which was age, and then a variable, X that is kind of shoe size, and we saw some kind of relationship that kind of went like this for a certain period of years. What we don't know is any of these, what three situations here is actually going on. Just because we get a relationship that's, maybe close to 1 here between age and shoe size doesn't mean that age is causing shoe size to increase. Y is causing the variation X. Doesn't mean that shoe size is causing age to increase. X is causing the variation in Y. Or is it some third factor? biological maturation that's causing age to increase and causing shoe size to increase. And so we have to be really careful when interpreting correlation that we're not ascribing causality to why these things are actually related. We can ascribe no causality to it. We can only infer that these two things are related. And then what you need to do is, if you want to find out if one thing causes another, then you have to put, at that point, you have to put X and Y, under the rigor of experimental, design. So now you're going to try to make one of them precede the other one to see if you can establish causality. Okay, so now you'll have X precede Y, and then control how you're manipulating X to see if it causes changes in Y. It goes back to the experimental design that we briefly covered, at least in the other course, the introductory course, the 680 course. And so all I want you to get from this video is that you have to carefully interpret correlation, and again, not ascribe causality to it. So I hope that clears that up, and thanks for watching the video.